my name is Justin Trump, and today we're going to be covering fractals and technology. So for the first part that's going will be Ollie. He's going to be covering computers, and then I'll be covering visuals, and then there will be Brianna. She will be covering software and video games, and then there'll be Anthony covering antennas and cell phones.
Okay, so from 3D design to music composition, the applications for fractals and technology is almost never ending. The same way that fractals changed the way that we looked at nature, art, and medicine, the introduction of computers to that concept change accelerated the analysis of fractals. So fractal analysis in practical terms is the concept of assigning fractal characteristics to a set of data, and computers being the powerful calculators that they are, they made that analysis that much more powerful. In the financial world, fractals are used to analyze market prices. The Elliott wave principle states that in the same way that fractals appear in nature with seashells and mountains, they also appear in market prices in the same way. They also appear in fractals also appear in data compression through image processing. The computer programs are able to look at parts of an image where the image is similar, and they break it down, and that process allows us to transfer data between each other really quickly. Fractals also appear in 3D rendering. These are both examples of that. And fractals appear also in algorithmic composition, which means that in music, if you've ever heard a pop song where they have the same 4 beats or so over and over again, that's a fractal because it's being repeated. So
that's incorrect.
And Justin, do you want to talk more about fractals and music?
Yeah. So continuing from what Ollie said about music, there are many applications for fractals in technology. And as he mentioned before, you can kind of use algorithms in music algorithms to compose music. And similarly to this, you can use that same process to create music visualization. And I have a picture right here. And these features can be found in music visualizers. And the basic idea is that you have a song, and they can all be different, and based off that song, there will be an image, and that image will change accordingly to that. And these complex images are created from simple formula fractals. And the idea behind this is that you use an equation, and that equation is able to repeat that process over and over. And then examples of this would be, right here we have the Atari Atari video music right here, and this is what it's able to display. The idea is that it uses some type of mapping, and it takes the music and uses the simple formula factors and displays the pixels on the screen. And then as time has gone by, the technology has evolved, and this is what it looks like now. And that wasn't the only thing that changed. In the 1980, there was the co-founder, Lauren Carpenter, and he worked at Boeing. And he wanted to create some type of 3D animated background for the new model planes to fly through. But during the time, there weren't any animation techniques at the time. So he came up with this idea to create a 3D terrain using fractals. And he got the idea from Mandelbrot. And he explains his process in this video.
Endless repetition, what mathematicians call iteration. It's one of the keys to fractal geometry.
The pictures were stunning. They were just totally stunning. No one's ever seen anything like this. And I just opened a whole new door to the new world of making pictures. And it got the computer graphics community excited about fractals because suddenly they were easy to do. And so people started doing them all over the place.
Carpenter soon left Boeing to join Lucasfilm, where instead of making mountains, he created a whole new planet for Star Trek II: The Wrath of Khan. It was the first ever completely computer-generated sequence in a feature film.
That's new.
Made possible by the new mathematics of fractal geometry. Lauren Carpenter.
In 1970.
So going off this process, the evolution of films and movies has greatly improved. And I'm going to list off a few movies that use fractals that you guys might be familiar with. There was the Star Trek II, there was Tron in 1982 and 2010. There was Star Wars Episode 3, Revenge of the Sith, and then there was also Transformers, Revenge of the Fallen. And I'll be passing it off to Brianna.
So fractals play a big role in video games. They play a big role in video games as fractals are part of, they could be a part of animation, visuals, and animation, as Justin and Ollie previously mentioned in the slides before me. Fractals are being included in rendering software. Fractals are included in rendering software that give the ability to create realistic 3D landscapes and terrains. And just imagine back in October 1958 when the first video game was created, and then this is actually it. And then now having the ability to create movies like Star Trek. It's called Tennis for Two. It was created by a physicist called William Heidenbotham. He was on the team of the first nuclear atomic bomb, and he created this. And now we have things that we could create. This is Vista Pro. So like in Justin's slide, it's a similar video of all the terrain and landscape, and fractals play a part in the landscape, terrains, and textures. And as you can see, fractals are being used throughout this entire video. And also, so right here, we have Hypothesis. So it's a fractal, it's an open source fractal flame editor, which allows users to use components like electric shape, which is loaded right here, to allow them to use effects in animation, and also, so here's some fractal art right here using rendering software. And a fractal flame editor is a program that Scott Davis invented with an algorithm that he invented using the language programming C. And then that's Electric Sheep, and that's Vista Pro. And that will be the end of our presentation as far as technology goes. Like Anthony, going on. So this is actually the application of Apotheosis being used in Fractal Flame, the editor, and here's the procedures that they use using the formulation of triangles to develop these things over here, and here's another part that they use in a rendering software. And here I'm going to pass it off to Anthony, who's going to cover it in communications.
So this is Nathan Cohen. In 1988, in Boston University, he discovered that using a Koch curve, which is right here, using a Koch curve would actually boost antenna signals. And this is so, the reason why is because it would expand the perimeter and actually make it so it would transmit and receive radiation way more efficiently than if it were to be just a single line antenna. This is his first fractal design, first fractal antenna design, and this is actually one that it's called the Sierpinski carpet. It's actually used in a lot of PCBs and cell phones. And PCBs are printed circuit boards, so it's actually made into the actual printed circuit board and put into your phone. And then this triangle over here is the Sierpinski gasket triangle. The development of the fractal antenna actually made it so you could use a whole bunch of different frequencies in cell phones. So that made it so that Bluetooth and Wi-Fi and walkie-talkie features were all able to process on the same frequencies, or had a longer range of frequencies in cell phones. So this made it possible. And so it made it so cell phones and laptops and the GPS and everything could use Bluetooth and enable Wi-Fi as well. And then another one of the more important ones is the HD television. The HD televisions actually use fractal antennas as well.
Are there any questions for us?
That's it on communication?
Yeah.
On fractal antennas?
Yeah.
Okay. Go ahead.
Any questions?
For the fractal antennas, what was his reasoning behind creating it the way that he did?
So basically, when he came from Boston University in 1988, he actually went to a fractal seminar, and then he he actually took an antenna from his ham radio, and he bent it to a fractal design, and then attached it to his ham radio, and it actually worked even better than it did before. And this was mainly because it actually transmits and receives radiation much better than if it were just to be a regular antenna.
Why? You're on the right track. Why?
Because it expands the perimeter of the antenna, so it actually is it's able to transmit and receive radiation much better than if it were just to be a straight antenna.
Almost.
Almost.
Does anybody else have any ideas on why that worked?
I think it's because of the design. It allows for more different types of ways to travel further and like a lot. It's a wider range. It's a wider range and it can take in more things.
It's basic length. If you can make it, the longer you make it, the more it's going to pick up, right? So here's the most important thing when it comes to fractals that is going to affect you from a tech perspective. Again, the longer whatever it is you're making, the more it's going to pick up, but you are limited by the amount of space. One more time, you're limited by the amount of space. So if you can't go outward, go inward. And how do you do that? Initially, people started coiling things, right? You see that still. But if you can turn it into a fractal, you can go almost indefinitely, down to the quantum level. Any other questions?
Is that why things always tend to get smaller and smaller and smaller over time?
Sure. Okay, bye.